Hello, class. You know, I can never tell if oh yeah, I'm recording, and my microphone is working. You know, that's the thing. This thing hanging down here, you can never tell if it's clicked off or not. I guess this is lecture 8, I believe it is. Although I may have already put lecture 8 up there, and this is 9. I have not got a clue. So you're probably looking at that circuit over there and thinking, oh my God, that's a really complicated circuit. What's in parallel? What's in series there? How in the world am I going to decombobulate, or is it discombobulate? I'm sure it's discombobulate, this circuit and simplify it so that I can actually figure out what the currents are through all of the individual resistors in that circuit, and also what the voltages are at those 3 nodes where the various things come together. Now, you probably noticed that I haven't drawn a big red dot around here, right? Because, of course, this part down here is going to be grounded. That's our ground. And then that, of course, means that this voltage up here would be 100 volts. But this is connected up to this very convoluted looking circuit. But that's the thing. We want to know how to take that circuit and then figure out what's in parallel, what's in series. How would I redraw that in standard schematic form so that I can then analyze that circuit best? And so that's what we're going to do. That's one part of what we're going to do today. The other part that we're going to do is we're going to look at, I'm going back and I'm picking up a couple small topics that we've sort of left behind along the way, because what I don't want you to think is that all resistances are from resistors. There's obviously resistances that are going to come from the wires that you're using. We use very low resistance and low resistivity wires in copper and aluminum. And that's what I want to point out here. Let's say that I had a wire. Now I'm going to take 2 wires. I'm going to have a wire that is, you know, a very small diameter wire that's very long. And then I'm going to have another very large diameter wire, right? The cross section there. I'm going to say that's half as long. Now, I know what everybody who already knows about resistivity is saying, hey, don't you have those backwards? No, I don't. So what I want to look at, though, is let's say that this is an aluminum wire. Now, actually, over in England and over in Australia, I had to learn to say aluminium because that's what they call it. They don't call it aluminum like we do here, like the element. They call it aluminium, and that you know, basically says that it's a little different. It's an aluminum alloy, or maybe they call aluminum aluminium. You know, the whole world is different, and so the other one that I've got here, the very thin, longer one, is going to be made out of copper, right? And I'm going to write copper, but really the sign for copper is Cu, isn't it? And the sign for aluminum is Al. So you should be familiar with those abbreviations for copper and aluminum, those being the 2 main conductors that we use in electrical engineering. Now, look at that equation up there. Resistance equals resistivity times length divided by cross-sectional area. Now, we know a couple things about resistance as far as the unit for resistance goes, right, in the SI system. And we know from our earlier discussion that that's a kilogram meters squared over seconds cubed amp squared, right? So we know that. And we know if R then equals rho times L I'm just going to put this in here, R equals rho, which is resistivity, times length divided by cross-sectional area, then we would see that resistivity, the units of resistivity, are going to be the units of resistance times the units of cross-sectional area, right, divided by the length. All right, well, let's do that. So that would be a kilogram meters squared per seconds cubed amps squared, right? Just put a fraction in there. That's going to be resistance meters squared over meters, right? Does everybody see that? So what you could say is that this meter right here is going to cancel out with one of those meters, isn't it? So we could say that this was an ohm meter. That's right. So it's an ohm meter are the units for resistivity. And that's what we end up getting them in. Now, I say ohm meter, but really if you look at the rest of this is going to add a meter. And if we wanted to look at the combination of primary units for resistivity, which is a dimension, it would be kilogram meters cubed over seconds cubed amp squared, right? Which is an ohm meter, isn't it? So that's what that's what resistivity. And I want to look at resistance for two different types of things. So the resistivity for copper, and I'm going to use the one in your book, although I don't really use this. I use 16 times 10 to the minus 9 ohm meters, or 16 ohm nanometers is the way that I usually look at it. But let's just do that. Let's say, but your book says that it is 17.2 times 10 to the minus 9 ohm meters for copper, right? We could also write that as 17.2 ohm nanometers, couldn't we? Does everybody see that? Because how many nanometers in a meter? We got to get rid of the meters, so the meters, so if I multiply it, it's going to have something anyway. I'll let you work on that. We're not going to go through conversion factors so much. I'm sure you're going to be going through a lot of, conversion factors, but everybody can see that's the case. Now, the other main conductor that we've got, and they point this out in the book too, and this is something I wanted to point out to you, is aluminum. And aluminum in the book, they also have a little bit high. That I think of it as 27 ohm nanometers, but they have 28 times 10 to the minus 9 ohm meters, right? And if I want to write that in ohm nanometers, it'd be 28 ohm nanometers. So those are the two, and look at the difference between the two. Now, you're not old enough to remember this, but when coaxial cable first came out in the early 80s, late 70s for, home TV connection, what happened was they originally did everything. The center conductor was in aluminum, and also the outside ground shield was in aluminum. But what they found out was that the aluminum oxidized too quickly, and then the center connector wouldn't work, and it just gave really bad connections. So what they do now, if you look at a coaxial cable, you'll see that the center conductor is copper, and the outside ground shield is still aluminum, because there's so much outside cross-sectional area that even at half, I mean, if you look at this is like 15, this is like 30, isn't it? So copper is basically twice as conductive as aluminum, right? Copper is twice as conductive as aluminum. Right, so always remember that. And now what I want to look at is what's the difference in these two things. So let's say that we wanted to have something that had the same the same resistance, and I'm using copper and I'm using aluminum, right? So if I had this longer piece of aluminum, let's say that this is going to be 2 millimeters. So I've got a 1 millimeter radius, right? So if I was looking at the cross-sectional area of that cylindrical wire that I've got, I would have pi r squared, right? Pi times 0.001 meter. And again, like I always say, always transfer things back into, I mean, don't multiply it by 1 millimeter, would you? No. No, you would multiply it by 0.001 meters so that you don't screw up figuring the thing out. And you always punch all of those things into your calculator too, right? It just takes a little bit longer, but it assures you of accuracy, you know? And we're more about accuracy than we are about precision. Precision, you can be totally wrong and still be very precise in your mistake, but you want to be accurate. So 0.001 squared times pi is 3.14159. Always remember, use pi out to 6 figures. Okay, times 10 to the minus 6 square meters. I'm probably saying times 10 to the minus 6 square meters. Does that mean it's a micron? It's a, no, 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 it doesn't. It's 10 to the 6, of course, refers to the 3.14159, and that's 10 to the 6 square meters. So, no. But I'm sure that you all know and understand that. So that's my cross-sectional area, right? So we want to find out the resistance of this. How long should we make it? Should we make it a mile? Let's make it 1 mile long. So I've got a 1 mile long piece of copper wire, and I want to see what the resistance, the total resistance of that 1 mile. And you're saying, well, 1 mile, why are we using miles? I thought we were using SI. That's right, but you know, we exist in America, so it's 1 mile. So how many meters would that be? That's 1,609 meters, isn't it? 1.609 meters, a kilometer. So 1,609 meters. So that's my length. This is my cross-sectional area. I know what my resistivity is. So let's just put that all together. So the total resistance of my 1 mile long copper wire that has a 1 millimeter, only 1 millimeter thing. Oh, you know what? I drew that on the aluminum, didn't I? Rather than the, let's use aluminum. So let's say that this is going to be my total for the aluminum wire. All right, so we'll put the aluminum one in there. 28 times 10 to the minus 9 ohm meters. Does everyone see why I'm putting the ohm meter one in rather than the ohm nanometers? Because nanometers is not meters. That's not the primary unit or a combination of primary units, is it? No. So our total resistivity times the length, now that's 1 mile, so 1,609 meters, divided by the cross-sectional area. And this is a really small cross-sectional area, so 159 times 10 to the minus 6 square meters. And that's going to give us, well, I'll pop it in here, 28 times 10 to the minus 9 times 1609 divided by 3.14159 to the minus 6 equals 14.34 ohms. I'm sure that's what everybody else got too, right? So this is for aluminum. That's going to be for an aluminum wire that's 2 millimeters in diameter, all the way down there. Yeah, 14.34. Now, let's do the other one, the copper wire. And I'm going to make the copper wire a smaller diameter than the aluminum wire. And I'm not just going to make it the same length. Let's make it longer. As you can see, I've drawn it longer too, haven't I? So let's make this 1 millimeter. So that means that the radius is going to be, in fact, why don't I just put a line? It looks like I might not get to that fantastic circuit that we're going to get to, but eventually we're going to get to it in just a little while. But I did want to pick up resistivity. I don't think it takes a whole lecture, so I will talk a little bit about this if we have room on the sheet of paper for me to do it. All right. So let's go back to this. So if we were looking at the total then, and let's make it longer, it looks about 1.5 miles, doesn't it? So let's put that in there. So the total for the copper, right, is going to be 17.2 times 10 to the minus 9 ohm meters, right? Times the length. And didn't we say that it was going to be 1.5 miles long? So I'm going to put 1.5 in there, and then I'm still going to put in the number of meters in a mile. Why multiply it out? Why not just put 1.5 times the meters in a mile? Now, that cross-sectional area is going to be much, much smaller, isn't it? Because the decrease in cross-sectional area goes down by the square of the radius, doesn't it? So 2 squared is 4, 1 squared is 1. So I would think that it'd be 1/4 of the cross-sectional area that I had here, 1/4 of 3.14 times 10 to the minus 6. So I'm thinking it's going to be something that's more like 0.8. And everybody should do this, right? You sort of think about this, and then if you put in your calculator, it says 6 billion, you know your calculator's wrong. But if we do that, if we say pi times 0.0005 meters squared, right? What is that going to be? And I think everybody can see, or can punch it in their calculator anyway. You get exactly that. You get, I'm just going to write it out as 0.785 times 10 to the minus 6 square meters, right? I'm gonna, so it's to keep it the same as 10 to the minus 6 here, 10 to the minus 6 here, right? So that's what we're gonna get, and we'll put it down here, 0.785 times 10 to the minus 6 square meters. And so we've got a longer and a much shorter thing. We would think that the, what would you think? Now this is about 1.5 times as long, but it's 4 times smaller, right? So it's 4 times smaller, 1.5 times as long. That's all going to add together. So that's 6 times, this is only 1/2. So I'm thinking that it's about 3. I'm thinking in my head. This is what you want to do. This is what engineers do. This is, I'm teaching you how to think. You're thinking to myself, okay, well, that should be about 3 times what this is. So I'm assuming that's going to be somewhere around 35 to 55. right, when I multiply it out. All right, let's put it in there. 17.2 times 10 to the minus 9 times 1.5 times 1,609 meters divided by 0.785 to the minus 6. And that gives us 52.88 ohms. And what that does is that confirms what we thought we were going to get, right? And this is how you want to approach tests too. You know, work it out sort of in your head for just a second. Just round things off so that you know what order of magnitude you're going to be working in. And the order of magnitude, of course, you know, here is going to be this. We figure it's about 3 times as much, and that's a little more than 3 times as much, and just sort of within the realm of what I thought it was going to be anyway, right? Still very small, a 1 mile long, you know, copper wire that's only 1 mil is still a pretty darn good conductor, isn't it? That's right. So, I still have a few minutes. So what I want to do is I want to look at this circuit right here. I think that I have enough room to actually redraw that circuit. I may be redrawing the circuit down here though, and you know, but or actually I could even redraw it down here. Yeah, why don't we do that? All right, so we're going to look at that circuit. So what's the first thing? What I want to do is I want to just, we know what this is. We know that's the power supply, and that power supply is going into, I'll use my green, that power supply is going into the rest of that network, that resistor network, isn't it? So really, what if I was just to cut that off right about there, and then just look at the resistor network and then hitch it back up to the 100-volt DC that I have, you know, in a minute. So let's do that. Let's say that this is my 100 volts DC that I've got right here, and then I'm going to come out of that. Now, I come out of it and I go in series to R1. So let's do that. So I go in series to R1. Now, I think that everybody can see that I've got a node here, node A. And node A has 1, 2, 3, 4, 5, 6 things that are attached to it. So what I want to do is I want to expand out node A. And that's what I'm going to do. I'm going to take node A and I'm going to expand node A out to just about the end of that sheet of paper. Probably should have gone to the end, but anyway, I'm going to leave a dash on there. We'll call that node A, right? So I've now expanded node A out. I still should put A on there so that you know that what I am doing is expanding that node out because it has so many connections, right? So I'm expanding node A out. Now, what is connected between you know, node A and node B, right? If we look at node B, node B has the 20 ohm, the 5 ohm connected to it. And those are the only two things that are connected. And where did I connect from? So they go from A to B. Let's draw those in. So I've got one that goes from A to B, right there. All right, so that's node B. Do we have another one that goes from A to B? Yes. Yeah. We have R3 that goes from A to B, right? We don't have any other ones, just those two. So this also is going down to node B. And there you go. Now we have node B. So let's draw node B in there. Right, that's node B. And what are those two resistors? Well, that would be R2 and R3. So R2, R3. Now, what separates node B from node C? I think everybody can see that it's going to be a resistor, right? And we know what resistor that is. That's resistor R4, right? R4 is going between B and C node. And so we know that this now is going to be the beginning of my C node, isn't it? Right? We've got a few things that are connected. Do we have anything that's connected from B to C? Yep, we do. We've got the R4 resistor, which is connected from B to C. Do we have anything connected from A to C? Yes, we do. We've got that R5 resistor. I'm just going to extend this out. We've got that R5 resistor that's connected from A down to C. So I'm just going to draw that in. That's R5. So we've taken care of this resistor. We've got R1 taken care of, R2, R3, R4, R5, all taken care of so far. Now, what separates off? Let's just look at this last node. I call it a null node, right? Because really we know that it's at 0. But, you know, we've got different things connected in there too. I'll draw that node in blue and I'll call that node D. But let's keep with C, right? So C now has another one in it, right? And that is R6. Oh, I went a little bit too far. I think I'll just draw that like that. There you go. That's my R6. So now R6 is taken care of. And where is R6 going? R6 is connected to C, right? So here is my C. I hope I haven't knocked that off again. No, here is my C. Yeah, nope, I'm still recording. There's my C node, right? So I've got my A node, my B node, and my C node all in there. And now let's redraw R6. I've got R6 is from C to D. So the other end of this, R6, is going to be going to the D node, isn't it? All right, so here's my D node. And then what is going? Well, we've got R7 that's coming from the A node to the D node. A node to the D node. And then, you know, really that node, sorry that I just drew that there because this node does extend over here. It's a short circuit, isn't it? So that part, that whole thing is one node. It's all a short circuit there. There's no resistor there or anything like this resistor and this resistor separates those two nodes. There is no resistor there. So I'm just going to draw that. Those are all connected, A to D. So the other one too is connected. And let me just connect all of those. And then this would be R8. And this would be R7. So there you go. That is our circuit now. Right? And I know that you're saying, well, that circuit looks very convoluted, Professor Granquist. I don't know if I can, yeah, let's just trim it down a little bit, shall we? So I'm going to say that this is my, I'm just going to break that out so we have a little room. This is my thing. This is going to go out into a resistor. And then it's going to go all the way across, and we're going to have one resistor drop down, two resistors drop down right there. Then we're going to have a resistor in between. Then we're going to have another resistor that drops down, another resistor in between, and then I'll just extend that out. And then two more resistors out here. And so that is what the circuit looks like. I'm just going to put the numbers next to them. That'd be the 1, this would be 8, this would be 7, this would be 6, this would be 5, 4, 3, and 2. And then, of course, the 1 is the first one, and that would be 100 volts DC. And so can you see how this circuit that I've got here, this is just something that you probably, you've looked at a printed circuit board, you see that there's different resistors going into all of these, different common holes here and stuff like this, and you realize as you're re-engineering the circuit that, this is how it looks, and then you can, but you can write it out in a schematic form, and you see that it looks so much simpler now, doesn't it? And in fact, in the next lecture, what we're going to do is we're going to go back to these nodes, right? We're going to look at that node right there. What's the voltage in that node, right? Stay ahead of me. We're going to look at this node here and find out what the voltage is at node B, what the voltage is at node C. We already know what the voltage is at node D, so we don't really have to worry about that too much because that is grounded, right? In fact, I'll put a ground in here too, but I think everybody can see that. All right, so we've simplified, we've looked at ways to simplify this, we've looked at resistivity, we've looked at calculating all of those. What we're going to look at next lecture is we're going to actually delve into, now that we know this, we're going to use what we know about current division and voltage division and voltage drops, and we're going to figure out what all the voltages are in this entire circuit. And not only that, we may also, I think we will, we'll probably look at all of the power that's being dissipated by each of these different resistors. Now you're probably saying, hey, that resistor thing there, what are the resistor values? I will put those in next class. All right? Okay. I'm not sure which lecture this is, but I'll meet you at the next lecture. See you there.